Hello, welcome to the sixth lecture of Project TCS. So in this lecture, I'll try to visit the concept of expander decomposition and pruning. And I'll also, and I'll talk about the definition, how to apply to solve some problems, and also an algorithm that computes the expander decomposition and pruning. So let me start. So basically, when you think about the divide and conquer, it is just dividing the problem into a smaller, tractable, and mergeable pieces. So for example, heavy light decomposition is also it is not in a trend, not a divide and conquer in a very narrow sense of definition where you just divide the problem into smaller pieces, but it can be thought as a sort of divide and conquer in a sense that it it divides the trees into a chain, and you know the chain is trackable. In chain you can solve problems more easier because so the chain is kind of easier 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 subgroup of tree because you can use binary trees usually. So that's why chain is easier. And chain is also mergeable because they are connected with light edges. And when you're considering a path, then you don't have a lot of pieces between them. And so when thinking about a tree, you have a lot of decomposition mechanisms like heavy light decomposition, centroid decomposition, blah blah blah. You have a lot of ways to decompose it. But when you think about the graph, it is not really decomposable. Like when you actually think about decomposing a graph, you require some special properties of graph. Like when like for example, in a planar graph, there is a small separator, so you can use the separator to decompose the planar graph into into a smaller pieces, but that doesn't hold for a general graph. And if the graph has a low tree width, then you also have a characteristic that's kind of a tree that then you expect from a tree. So you can also decompose that kind of that, but that's not what happens in general. So in that sense, expanded decomposition is interesting because it is the decomposition of any graphs. It decomposes any graphs into smaller, possibly not smaller, but anyway, into a tractable and mergeable pieces of expanders. So yeah, expanders have good properties. We'll talk about it later. So it is more tractable, and expanders are well separated, so it is more easy to merge them. So before we start, let's get to some definitions. They are not hard. For a graph, a cut is a vertex subset where the subset is not empty and the subset is also not a full set. So it's a division of the graph into two pieces where both pieces are non-empty vertexes. So and also G bracket S is an induced subgraph of S in G. So and for to disjoint set AB subset of V vertex set, EAB is the set of edge where two endpoints lie in A and B. So it's like this: you have A, you have B. I think I have to write like this. Then this kind of edges are in EAB. Yeah. So yeah, okay, let delta S be the value of the cut. So it is the number of edges that goes inside and outside of the cut. S, oh, V minus S. I hope I'm doing everything right. So yeah, they are the cut. And the number of such edges are the value of the cut. And the volume of the cut is defined as a sum of the degrees of the vertex subset in the cut. So we define the volume thing because we want to like we define the volume thing because we want to like do the recursion because decomposing a large graph with at vertex with large degrees is different with decomposing a graph with small degrees. So even though your decomposition is not balanced in a sense of vertex cardinality, if the decomposition is balanced in a sense that it reduces a certain number of edges, then it is fine. So that's what we are trying to do with the volume thing. The conductance of the cut here it becomes a little bit scary, the conductance of the cut, but it is not a hard concept, and per se it doesn't relate to the electrical or spectral thingy per se, but it's not really that. But anyway, so it is basically something like this. When you think about the cut, the problem with cut is that if the graph is really dense, then the cut is likely to be very unbalanced. So like if the graph is a complete graph, then obviously there is an obvious cut and it includes only one vertex. And that's not what we exact, that may not what we exactly want to do. So yeah. So if we want to see how well connected the graph is, then the usual definition of connectivity fails at that point. So what you do is you divided it by the size of the volume, so you balance it. So so in that case, the cut, although it has a small value size. So I mean, you think about the complete graph, then it has a small value of cut. But when you think about the reciprocal of the minimum of two small volumes, then they are large because they are unbalanced. So you're trying to keep some balance on it. So that's kind of an intuition of why you take a conductance. So yeah, so summarizing, it means that it's just well balanced. I mean it's just a better it's just a better notion of how well connected a graph is. So for convenience, assume that when we talk about the cut S, that then the volume of the S is always smaller than its inverse. The conductance of the graph is the minimum conductance of all cuts. So yeah, so it means if you want to separate some cost, then you have to pay a lot. Yeah, I think this is obvious. Like, I think this is obvious in a sense that when you think about the when you take down the volume, and when you just think about the minimum overall value of cut, then the minimum cut is obviously defined like that. So that is an obvious definition of how you extend the definition of conductance of the cut toward the conductance of the graph. So if the cut does not exist, we conventionally call it 1, but it doesn't really matter. A graph is a pi expander if the conductance is at least pi. Yeah, so graph is 3 connected when the minimum cut is at least 3. The graph is pi expander when the minimum conductance is at least pi. So it's just the same thing. So let's figure why expander is good. So expander is a well-connected graph. We want to say expander is a well-connected graph, and that property makes several problems easy. Actually, this is kind of non-intuitive because when we usually do the divide and conquer, we want a graph that is least connected, like trees. Trees are very unwell connected. So we usually want that sort of thing, but this is interesting because it's the exact opposite. So first example is the decremental spanning forest. When you delete a tree edge, like like suppose you are maintaining a dynamic graph and you want to delete an edge and you want to still maintain a spanning forest. If you delete a non-tree edge, then everything is fine. But if you want to delete a tree edge, then you have to alter the spanning forest. You have to take one non-tree edge and it may turn it to a tree edge. So yeah, so basically you want to find new edges that connect to components, and you want to recover it from the heap of back edges. So how should it gonna do? If the graph is an expander, then the back edge reconnects the graph with pi probability. So random sampling just works there. So yeah, I cannot write down the formula because when I write ABC, it works like this. But yeah, but anyway, it's not hard to figure out. So yeah. So another example is the global minimum cut. As we talked about it earlier, in a dense unweighted graph, cut is highly likely to be unbalanced. So with this intuition, the global minimum cut in expander can be thought as a cut finding where the smaller size is really small, like and most polylog and time that much small. So it's kind of exponentially small. So in that intuition, so yeah, you just you just use the problem of the cut problem inverse to attack the global minimum cut problem. So that is the rough idea of how Jason Lee computes deterministic mean cut in almost linear time. But of course, it's not everything. It's just a tiny part. Like it's just a tiny part of all more ideas and all more detail. But anyway, that's how it starts.
I think your screen is not mirrored in our view, so you may write. You may use the screen freely.
This?
Yeah.
Not mirrors?
In our view, at least.
Okay. And okay. Usually those applications require polylogarithmic reciprocal. Yeah. So I think you can just assume that pi is that order throughout our lecture. So okay, so that's great. So let's get back to what real expanded decomposition is. So given a graph and two arguments, an epsilon pi expanded decomposition is a partition of a vertex set where each induced subgraph is on pi expander, and there are at most epsilon fraction of edges going through the different sets. So that is the expanded decomposition. So I think the definition is really simple. It's just partition. And there is also an easy algorithm that computes the expanded decomposition. So given any phi in interval 0 to 1, pi log m dot pi expanded decomposition exists. And what you do is just find the cut with minimum conductance and just recursively decompose the subgraphs. So if you just, so you just, like, if you have a graph, you just find the minimum conductance cut and you just divide it afterwards. Divide it. So it's just really simple. It's just, you just recursively divide it until each partition becomes an expander. So in that case, if you count the edges going through different sets, you have that formula. So with that formula, you can easily prove that epsilon is at most pi log m. So it's kind of just like small to large kind of thing. It's just, the proof is just like small to large kind of thing. So the remark is, for fixed pi, you cannot get better epsilon bound. However, the problem with this simple algorithm is that it is really slow because the minimum conductance cut, we'll call it sparse cut, it is NP-hard. So this paper finds a phi log cubic m times phi in time m log quartic m divided by phi, and this is a randomized algorithm. So so going through some history. So the first polynomial time algorithm for expanded decomposition just finds an approximation of minimum conductance cut. So if V is not a phi expander, you just find order T of phi sparse cut instead. So you got like phi, you got square root of phi more overhead, but yeah, that doesn't really matter because it seems very hard to get a phi log m decomposition. But the issue is that if the sparse cut is unbalanced, then the recursion that might grow to pi n. So it results in at least quadratic algorithm. So what does it mean is, like, say if you have an approximation algorithm that runs in linear time. So running in linear time is good, but when you have that, then we are having the recurrence of T m is T a plus T n minus a plus order of n. And if this is not balanced, then this just can't go better than its squared version. So yeah, so we want a balanced decomposition. We want a balanced cut for this matter. Here we'll call the cut balance if the smaller size has at least polylog n size. So, and then here comes the near linear time algorithm for expanded decomposition, and it uses a spectral method for sparse cut approximation. So the main question is how to get a near linear time with unbalanced cuts. So this algorithm finds a balanced cut, or if it's not balanced, then the larger size is contained in some expander subgraph. So it's something like this. So it avoids recursing in that point. Like if you have a decomposition that is unbalanced like this, you have this, no, wrong drawing. If you have an unbalanced decomposition like this, then you know that this larger part is contained in some expander subgraph. And you can't even see that, but interestingly, that is also strong enough. So when you know that there is an expander subgraph that contains this S, then you don't have to find the decomposition afterwards. You can think this as a sort of expander. That also gives a great opportunity for some approximations. So I mean some algorithms. So it does not really find expander decomposition because this is not an expander. It is just contained in some larger expander, but it is enough for many applications. And yeah, here epsilon is pi square root pi polylog m. Yeah. So I actually asked Richard Peng about like testing this lecture, and he didn't like that I was kind of dissing this algorithm. So he wanted me to appraise this and give what it deserves. So anyway, that is the history, and we'll go to expander pruning here. So it is a different thing. It is a different thing with expander decomposition. So let's revisit the case of the decomposition of spanning forest. So we can think about two cases. The tractable case is expander. Using the expander decomposition, we can maintain spanning forest for each partition, as we mentioned before. And if there is a cross partition edge, we don't have a lot of them. They are only polylogarithmic, so we can just kind of naively consider them, but not really. But let's not get into the details. But unfortunately, the removal of the edge alters the conductance. It changes the graph, so it changes the conductance and it breaks the expander decomposition. So the goal is to maintain the expander decomposition dynamically, given edge deletion queries. So it's the decremental expander decomposition. And why don't we consider like fully dynamic expander decomposition? Because well, I don't know, but I have a feeling that many problems that it solve the expanded decomposition is just decremental. Like you just have a fully dynamic version and somebody just reduces it as a decremental version, because the incremental version is usually quite easy. So yeah, that's why decremental usually matters. But that's just my impression. I don't have proofs for this claim. So what you do is, if you remove an edge, it hurts the expander. Like you think about how local it is. Like if something is infected, then it decays in the part near where it's impacted, where it is hurt or being infected. So expander also works in similar local way. If you remove an edge, then it hurts an expander. So like, so it's something like this. So if you have an expander, you remove an edge here, then this part is getting hurt. If you have an expander, you remove this edge, this part getting hurt, and that part you have to prune it. You just identify where it gets hurt and you prune it. And if you prune it appropriately, you can maintain that the non-pruned part is an expander. So that's what expander pruning is. So for each expanders in the expander decomposition, you maintain a pruned set where if you remove them, the graph is guaranteed to be an expander and P grows sufficiently slowly, so you don't have to alter a lot after each queries. So the result is like this. I won't get into the actual number crunching, but basically it means the volume, it doesn't grow fast in an amortized fashion, and each graph is an expander decomposition. And the total time for update takes logarithmic time. So when you go back to decremental spanning forest, P is incremental, so you can maintain a spanning tree easily there, and the graph remains an expander. So decremental method works. So you maintain the part where you delete an edge with a decremental algorithm, and if you increase the prune set, and then that part you maintain a spanning tree incrementally. Yeah, let me take a break. I think I'm tired sleeping. So let's go back in 10:40. He's not sleeping, but anyway. Yeah, so let's go back to the algorithm that solves the expander decomposition. We won't get very deep to the expander pruning actually here. So this paper uses a flow-based method for sparse curve approximation, and it uses a push reliable flow algorithm for in its deepest part. So yeah, it improves the n to the small O1 time bound on NSW 17. It was my paper for season 1, and it is really complicated, as you know. I think you don't know because I just skipped all of them. But when you take a look at my lecture notes, then it is just prohibitively like tedious. So yeah. So anyway, this is much simpler, and this also improves the time bound. But this is not deterministic. This uses a randomized. Yeah, that is not deterministic. Sorry. So this is also a randomized algorithm. So yeah, this also looks slightly practical, and also believes this is implementable. Maybe, I don't know. Yeah, I can't, but somebody can maybe. So SW19, I'll just call it like that. So it finds a cut that is either balanced, or it finds an unbalanced cut such that the larger side is nearly phi expander. So nearly phi expander can be easily processed. So nearly phi expand nearly phi expander can be easily processed. I'll just get back to it later. So yeah, unlike the previous one, it does find the real expander decomposition because it doesn't just settle on the nearly phi expander. It modifies it to be sort of balanced, or it doesn't recur. So the algorithm consists with two major components. One is cut matching game and the other is trimming. Cut matching game is an approximation algorithm for the sparse cut. We call the sparse cut approximation algorithm as cut matching game. For why is it have a name game on? I'll just talk about it later. So anyway, it certifies either it is an expander or it returns a sparse cut with conductance of phi log square m. So yeah, so it has the property where the cut either is balanced or the larger side is a nearly phi expander. So what is nearly phi expander? I didn't explain this, but just think it as something nearly phi expander. It is not phi expander, but it's something near to that. I'll explain it later. Trimming takes the nearly phi expander and it returns the subgraph A prime that is the real expander. Here A prime is sufficiently large so that V minus A prime remains small. So yeah, if the A prime gets extremely small, then like our strategy is something like that. We take if the cut is unbalanced, then the larger side is a pi expander. Like if the cut is unbalanced, the larger side is nearly pi expander. And what you do is you just trim this to be a phi expander and you recurse here. You recurse in only one part. So if you take a nearly phi expander, you just trim it and you recurse it on the other side. Then you will have a nice phi expander here. So the thing is, this should be sufficiently large. So if it is tiny, then it is also unbalanced. So it just changes parts. It's also unbalanced. So it should be sufficiently large, and it should also kind of preserve the conductance. I mean, we return the sparse cut of conductance phi log square m. The order and lead should be retained. So yeah, that is the two major challenges of the trimming, and the time complexity is also and most the matching game. And as you see, both are pretty efficient. Both are nearly linear, and it just have another log factor. So we can see they are pretty fast algorithms. So we get back to the real algorithm definition. Given a graph, we check if phi g is greater than 6 pi or not. This is called the matching game. If it is, then we find an expander, because if it is greater than 6 pi, then it's obviously greater than pi. So we're over. Otherwise, we have a sparse cut. And if it is not balanced, then the larger set is the near 6 pi expander. So we use the trimming to make it a phi expander. And yeah, we recurse in the stop problem with size n most m divided by log square m. So if the sparse cut is not balanced, then we are done. We just split it into two parts and recurse. If it is not balanced, then we use trimming. So we don't recurse on larger part and we just recurse on the smaller part. So assuming all the sub problems, we can prove the main result. So the correctness is kind of obvious. The time is also kind of obvious. The all cuts are balanced. The algorithm has maximum log third recursion depth. It's because if basically you need log square caps to make it 2/1. So you multiply log square to log. So you have log third m, and each sub problems are disjoint. So you have m log m divided by pi multiplied by log third, so you have log quartic. Yeah, and it's guaranteed that the training step doesn't grow so hard, and the training step doesn't blow up the graph, and it just reduces the size of the instance into sub polynomial. In the constant size bound, so the bound remains. Edge count, we have log square m approximation on sparse cut, and yeah, training doesn't change this. So if we combine this with previous small to large observation, we just multiply log square and we're done. Any questions? So yeah, we have two sub problems that is not resolved. One is cut matching game, and one is the one is the trimming step. So the cut matching game is the abstraction of some certain optimization paradigm in sparse cuts. So yeah, it is a traditional, like it is a known result, and it is an old result. It is not very old, but it is a sort of old result. So in this paradigm, there exists a log square n near linear time approximation algorithm for sparse cut. Here, log square n means the approximation factor. Yeah, I think this is a rather complicated, or yeah, this is very complicated. Like technically, this is very complicated, and the key idea is not also that easy. So I'll just provide a high level idea that is probably related to this lecture. In a graph, there is a cut player and matching player. They are playing a game. That's why we have the name cut matching game. So cut player thinks sparse cut exists, and she want to prove that the sparse cut exists. So she gives a bisection of a vertex set. Matching player thinks G is an expander. So M thinks G doesn't have a sparse cut. So what M do is she finds a large matching between two given bisection, between the bisection that C had given. So yeah, yes, it's not intuitive why large matching counters that the sparse cut exists. Like why large matching say implies the expander thing. But anyway, let's just move on. So the thing is that if M always finds a large matching for log square n terms, regardless of the strategy of the cut player, then we can take the union to prove that G is an expander. If M fails in some term, then C can take a small matching. And it can be used to find the sparse cut, because the matching is the flow. And a flow is dual to some cut. So you use that cut, and in that case, if C has a good strategy, then the bisection and then the failure to find the flow in some bisection can be extended as a sparse cut. So how to find that magic bisection? So if everything should work, there should be a magic bisection where the failure of matching player proves that the sparse cut exists, and vice versa, that the success of the matching player proves that shows some expander subgraph. So how to find bisection? It uses spectral method that does kind of a sampling, which is like adversarial to the matching stack that M had currently provided. So yeah, I won't get into details because I don't know this very well. I think if you want to know more about this, you can just refer to the paper that I think that Vajrani wrote in 2009. How to guarantee a near 6 pi expander. This is also not guaranteed by HRB 909. So the author needed some modification for it, but it is in appendix and it is not in the main paper. So I'll just keep it. I don't understand that very well too. It's also complicated. So yeah, that's all. we will get to trimming. Trimming keeps the expander decomposition balanced, and it is the key technical contribution of this paper. So assume all the volumes are with respect to G, but not with respect to induced subgraph. So the volume, when given a vertex subset, volume is a fixed function. So it doesn't depend whether G is a subgraph, induced subgraph, whatever, we don't care. It is a fixed value. So we define Neal expander. Neal expander is, so a subset of vertex is a Neal expander when you can count an edge that goes outside the induced subgraph. So like the usual definition of the conductance of the cut is it is like the usual definition of the conductance of the cut is self-contained, so it doesn't reply to it doesn't care on the global definition, I mean the global edges or something getting outside of it. But here you use the global edges that goes outside the A. So note that A is pi expander when the cut size is like not V but A. Yeah. So Neal expander is a relaxed definition where edges outside the induced subgraphs are counted. So trimming finds an A prime such that it finds an A prime such that A prime is 6 pi divided by 6 expander. Yeah, I think this is correct. Yeah, it is just equivalent to 5 divided by 6 expander. So the best scenario is where we don't do any trimming and certify the Neal expander as an expander. So we just don't want to do trimming if it's possible. Let's try it. Suppose not. So A is a phi Neal expander, but not 5 divided by 6 expander. Then the relaxation is heavily abused. So what does it mean? So when we talked about expander, S V such that Neal expander So it's easy for a graph to be a Neal expander because this term is increased because it goes outside the A. So if the set S is something like so if you have a set so if you have a set S like this, and if you have a set A like this, and if we have a like set V like this, then like expander only consider these edges, but Neal expander also consider these edges. So the term is easier to grow. So this term is more easier to grow. So it's easier for an expander it's more easy to be a Neal expander than to be an expander. So this is where the thing is really abused. And if the A is pi Neal expander, but not pi divided by 6 expander, it's a difference over six times. So it means then something is really wrong. So we did a relaxation and it changes a lot. That means our relaxation is abused. Then how can it be abused? If there is a lot of edges going outside the set A, then it means the relaxation is abused. So it means that some cut have more edges going outside of A. So yeah. So it means the S, this is S B minus A. How to say? This is B minus A. This is B minus A. And this is A minus S. So there are more edges going outside than edges inside there. So that is where we have a difference. So yeah, we captured the gap with flow algorithm. So consider the following flow instance. So each edge is going outside from A is replaced to the supply. Each vertex have demand from sink, and each internal edge have some certain capacity. I'll take I'll take some questions if you have it. Let's just continue. Yeah, so yeah, let's draw it again. Yeah, let's draw it again. Yeah, so this is the supply, and this is the sink, demand. Demand is degree. Supply is 2 pi per each edge. So yeah, and obviously the sum of supply is the value of the cut multiplied by 2 over pi. So the claim is if A is not a phi divided by 6 expander, then max flow does not satisfy all the supplies. So we do a proof, and yeah, it means there exists a set where it goes out from outside more than inside, and like from the outside, like there is a set where it goes outside a lot from B minus A, but it goes less from the less in the inside, A minus S. Then when you provide a large number of flow here, then it doesn't pass it through all outside. Some of them are necessarily stuck here. Some of them are necessarily stuck here. So of course there is some degrees, but anyway, that doesn't change things significantly. So some things are gonna be stuck here, and it means a lost supply. It means a lost supply. S is wasting some number of supplies. So something is lost on S, and therefore the maximum flow does not satisfy all the supplies because it eats a lot and it doesn't produce that much. So in other words, if you take a contraposition, if the maximum flow satisfies all supply, we can prove that A is a phi divided by 6 expander. Otherwise, we fail to direct all the supply. So here we do a funny thing, like, so we now have a notion that if a maximum flow satisfies all supply, then A is a phi divided by 6 expander. Then what you do is this: you have a source and you have a sink. And you have a problem because the source did not routed all the supply toward the sink. So there is a minimum cut here. Then what you do is just you add all of these, like you have A, you have B, and you have S here. Then what you do is you just put them out from the V. Then here was the bottleneck. here was the bottleneck. So the bottleneck is all saturated. So you use the same flow and just you add this to the direct connection of the source. Then yeah, all supplies are saturated. So since this was a bottleneck, so the thing we wanted that the maximum flow satisfying all the supply is automatically satisfied. So yeah, we just get a subquadratic trimming. You use Dinic or Madry to compute the maximum flow. And if the cut is not trivial, prune the source side cut. And then it's over. You can compute the trimming with one step of maximum flow. Any questions? Yeah, okay, so that's all the ideas. That's the key idea. So let's bound the size of the source side cut. Note that the source side cut must have its thing saturated, but because it's a cut, and blah blah blah. I think yeah, this is boring calculation. So anyway, the takeaway is it does not blow up. It does not blow the original cut, smaller side of cut into something very huge. So you don't have to worry about that kind of pathetic cases. Let's also prove that the conductance does not blow up, but yeah, it's also just a routine calculation. I don't think it's so hard to prove. It's easy. So anyway, yeah, we established that trimming is expanded decomposition. Trimming implies expanded decomposition. But we didn't do a, but we don't know how to do a near linear time trimming. So how do we, because Madry is slow, Madry is anyway slow. Like it is something like m to the 7/10, something like that. It's not near linear time, it's fast slow. So if you want to achieve near linear time, you need to use approximate max flow techniques, because when you go back to the original flow construction, it is not tight. It is not a tight flow. So you can, there is a little bit of room for approximation. But in that case, you have to prune, you cannot prune this one time. You have to prune this multiple times. You have to prune it like log time. So yeah, so if we have an exact cut, exact maximum flow, then we can prune it for only one time. But in this case, you have to prune it for like log time. So yeah, and it does converge, we can prove it. So this gives an extra overhead, and you cannot compute everything from scratch. So you have to design an efficient algorithm that does not compute flow from scratch over after cut removal. So if you remove a cut, then you automatically rewrite the previous flow into the new cut that you have approximated. So yeah, so how to do it efficiently? It just uses the push reliable flow in a modified way. So it's not really easy, and it's also technical. It's complicated, and I don't understand, to be honest. I think maybe it's time to learn push reliable flows, but anyway, I don't know it, so I'll skip it. Yeah, so trimming implies expander pruning. I can't get this into details, but high level idea is that this is just like, if you think about the definition of pruning, then we are just pruning here. Trimming is just pruning. It's just similar thing. And yeah, it just works like that. High level idea is just applying a near linear time trimming after edge removal. So yeah, that's all, that's everything. And if you want, I don't think I did a very good job in explaining this talk. So if you want a better explanation, there is a really nice 2 videos from the author of this paper. I really like this. It's a very nice explanation. So please take a look. They are nice, and you can learn what kind of things, expander decomposition and pruning those. Also, I think I almost talked about everything that the video conveys. So yeah, thank you for the listening, and see you after the hour break.